this is functional design patterns. Patterns is becoming sort of a dirty word, especially in the functional programming community. So some people, you might want to call them principles. Yeah, I don't know. How about practices? I don't know. It's hard to find a good word for these things. So I'm just going to call it things that functional programmers do a lot. Okay. So rather than just labeling everything. Now this is an introductory talk for people who are new to functional programming. So if you're an expert already, you might not find this talk very interesting. So this is definitely a beginner's talk. My name's Scott Wlaschin. That's me on Twitter. I have a website, f#forfunandprofit.com. Which is, as you guessed, about F#, and a lot of the examples I'm going to use are F#, but the principles are really for any functional programming, including JavaScript, if you have to. So this talk is going to be one of those things where you whiz through thousands of things. It's like going to a tourist, a city, and you just go on a tourist bus and you see everything in 5 minutes. You don't really get a chance to stop and look around. So that's what this talk is going to be. I don't expect you to understand, everything. I just want to kind of demystify things, show you some things, tell you about monads so that you're not too scared about monads. But the idea is that once you see, hopefully it's not too scary, and then you can actually maybe investigate it more yourself later on. So this is, like I said, it's a whirlwind tour. Please don't worry if you don't understand everything. It's really just to sort of get a big picture of everything. So just a little bit about me, first of all. I have been programming a long time. This is me when I was a child. That's how long ago I've been programming. And I used to be a normal programmer, like people. And then I got introduced to some functional programmers who kind of assimilated me. And they took me to this ivory tower. And of course, at the very top of the ivory tower are the Haskell programmers. And the F# and the OCaml programmers are a little bit further down, and the Visual Basic programmers are right in the basement. And the Lisp programmers are on another planet altogether. So that's me. I'm in the ivory tower. I can now speak about functional programming and use long words, and I can actually say with a straight face, a monad is just a monoid in the category of endofunctors. So that's a very scary. This is the kind of terminology that functional programming people use all the time, which I think is really off-putting, and I really don't think people should say this kind of stuff. But, it does actually, believe it or not, it does actually make sense. And we'll see, hopefully, by the end of the talk, you'll have a kind of a little inkling of maybe what even these things mean. So, functional programming design patterns. Now, we're all familiar with the object-oriented design patterns and the principles, like the solid principles and open-close and dependency inversion factories and strategies and all that. So there's all these principles and patterns you use in OO. And when you got assimilated into the functional programming people, they give you these things to say. And every time someone says, well, how do you do the single responsibility principle? You say, that's functions. And then you say, well, how do you do open-close? You say, oh, that's functions. How do you do dependency inversion? That's functions. 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 Resistance is futile, functions. So that's very unhelpful. It's not very useful to say. I mean, it's true in a way that everything is functions. It's not very helpful if you're trying to learn functional programming. But the point is that functional programming, the patterns that you use are very different. So yes, everything is a function. Now what? How do you do the kinds of things? How do you build bigger programs from these functions? So there's various patterns and tips and practices that you use to do functional programming, and that's what this talk is about. So there's no point trying to map, how do you do a factory pattern in functional programming? It doesn't make any sense. But there's different patterns for the different challenges you have. So I'm going to talk about 3 core principles of functional programming. And then I'm going to talk about functions as parameters, which is a really important point. Composing functions with multiple parameters, that's another important point. I'm going to talk about something called bind. And I'm going to talk about something called map. And then I'm going to talk about monoids. And unfortunately, there's not a friendlier word for monoids. That's the kind of word there is. Now, these words sound very scary. There's a lot of scary terminology. And hopefully, I'm just going to try and demystify that. So the words might be scary, but the concepts are actually pretty straightforward. So depending on the programming language you're using, some of these patterns are sort of built into the language. Obviously, functional programming languages like Haskell and F# and OCaml, you can do this a lot of these things are sort of built in. If you're using JavaScript or or PHP or something, you have to do a lot more work. But like I say, they're general principles. All right, so what are 3 core principles? These are my favorite ones. There are more, and if you're a Haskell person, you probably don't agree with these, but these are my ones. The 3 principles, first of all, functions are things. Okay, this is a different way of thinking about functions that you're used to, as if you're used to OO. The second thing is you use composition everywhere. Everywhere is composition. And composition is like Lego. It's building bigger things from smaller things. That's all it is. But that's the fundamental design principle in functional programming. And thirdly, if you're doing statically typed functional programming, types in functional programming are not the same as classes in OO. So again, there's a mismatch between what you think. If you're used to OO, you have to kind of change how you think about these things. And let's say some functional programs are very big on things like referential transparency and purity and all this other stuff. I actually don't think that's the most important thing. I think these are the most important things to understand, and the other stuff sort of comes later once you get this down. So the first thing, functions are things. So functions are things, they're not attached to classes like in OO. I like to think of them as little bits of railway track. And there's a little tunnel, a tunnel of transformation, and something comes in, like an apple, and it comes out as a banana, all right? So that's what a function does. It's just a standalone thing, and we say this is an apple to banana function, apple, arrow, banana, all right? So that's it. That's what a function is. What's interesting is that in most programming languages, you define, given a name to a number, like z equals 1, that means there's a little box and there's a number in it, and you've given it a little label. Now, in a functional programming language, when you define a function, like add 1 equals x plus 1, you define a little piece of railway track, and you give it a name. Now, what's interesting is that in most functional programming languages, the keyword that you use to define numbers and strings is exactly the same keyword used to define functions. And that's not a coincidence, because functions are treated just like numbers and strings. You can put them in lists, you can pass them around, you can return them, you can do all the stuff that you do with numbers and strings and dates and stuff, you can do them with functions as well. So, here's a function. This is a function that takes an int as an input, but it returns a function as an output. So this is a function that returns another function. You can also have a function as an input. So here's a function. The input parameter is another function. And then maybe it spits out an integer as a result. Or alternatively, you have a function which has an input as an int and an output, but there's some extra parameter which kind of controls how the whole thing works, like sort of the strategy pattern, if you will. And that's using a function as a parameter. So that is, because functions are things, this is the kind of thing you can do with functions, right? And what's interesting is using functions as inputs and outputs and parameters, that really is the foundation of functional programming. And what's interesting, you can build really complex systems from that. I mean, that's the simple thing, but if you have a function that returns another function that returns another function that takes another function as a parameter, you can get really complex, obviously, but the principles are very basic. So, first principle, composition everywhere, or the second principle rather. What is composition? So let's say you have a function which turns an apple into a banana, and you have another function that turns a banana into a cherry, and you want to connect them. How would you do that? Well, it's pretty obvious. You just kind of connect the two pieces of railway track. If you've paid for Brio or something, it's really obvious how this works. And when you've done that, you now have a new function that turns an apple into a cherry. So it's kind of really obvious how this works, but this is the key thing. A couple of interesting things to note, though. This new function, which turns apples into cherries, you don't know how it was built. It was built from smaller functions, but you can't tell. Right? So you've got abstraction, you've got data hiding kind of already. And what's also interesting is the banana's disappeared. Right? Where did the banana go? So the fact that you needed a banana at the low level might have been important, but at the higher level, you don't care about bananas, right? So this composition thing is very cool. And so you can use this composition to actually build big systems from small systems, and it works at all scales, from the tiny scale up to a large scale. So you start with a very simple function, like uppercasing a string. The input is a string, and the output is another string. You can take all these low-level operations and maybe combine them into some sort of service, like an address validation service or something. And there's an input, which is the address, and the output is the validation. And for people, by the way, service might be not a familiar word. So for people under 30, it's just like a microservice, but without the micro in front. You have to be over, if you're over 30, you'll know what a service is, but if you're under 30, it'll probably be too an issue. Right, okay, so we've got these services, we kind of glue them together into some particular use case or scenario or workflow, whatever you want to call it. And there's an input and an output, and then you take all these use cases and you maybe want to make a whole web application from them. And so the web application has a HTTP as input and HTTP as output. And inside the web application, you have all these different functions, these use cases, and you have a router or a dispatcher or a controller, whatever you want to call it, that decides which one of these functions to call. So there's your entire web application built from smaller functions. And this is totally doable. There's many functional programming web apps which have no objects in them whatsoever. So you can kind of see that composition is fractal. Fractal's not really the right word, but it sounds cool. It's self-similar. The same kind of approach is used at all different levels of an application. Right, so number 3, types are not classes. So if types aren't classes, what are they? Right? They're sort of like sets. So I've got a little Venn diagram down there. Here's a function, and it's got a set of all the possible inputs for this function. It's like a box with all these possible things you could pass in. And there's a set of all the possible outputs for this function, right? So a type is just the name we give to that set. That's all it is. So a type is just a set of values, in a sense. So for example, if a function can take any integer, we say that's integer type. If we can say it will spit out any string, we call that string type. If it can take any kind of person, we say it's the person type. Now, these can be kind of virtual things. Obviously, we can't have every single person in the whole world, but we can define a type called person, which is, in a domain modeling sense, it represents all the kind of people that we can handle. And we can have a type fruit, so that it doesn't even have to be real things. And what's interesting is, because it's just a set of things, you can have a set of functions. So this is the set of all functions that turn fruit into fruit. So this is a fruit-to-fruit type, right? So this is the kind of thing that's hard to do with object-oriented programming. You have a type which represents a set of functions. All right, so that's types. What's cool about types in statically typed languages like Haskell and F# is they can be composed too, just like functions. And we call this an algebraic type system, or a better word would probably be a composable type system, because again, you can build bigger types and smaller types. And again, composable like Lego. So if you know how to use Lego, you know how to use an algebraic type system. So there's basically 2 ways of building bigger types and smaller types, and you use and you use or. Now, that might sound weird. What do you mean anding 2 types and oring 2 types? What does that even mean? So let me give you some examples. It's important to note, by the way you can do this is because there's no behavior. It's just data, it's just sets, right? So just like you can have a union of 2 sets and the intersection of 2 sets, because there's no behavior, you don't have to worry about trying to keep the behavior as you chop and slice these things. So if you've got object-oriented thing, you can't really combine 2 classes together very easily, because how do you know what the behavior is between, when you have an intersection of 2 classes? So the and types are very familiar, because we're normally called record types. So let's say you want to define a fruit salad type, and you say, well, I need to have 1 apple and 1 banana and 1 cherry. So it's a tuple. We call these tuples. We call them structs. We call them records. There's lots of different words for these things. In F#, you might write it like this. It's just, you can see with curly braces. So it's a bit like, it's just like a struct or a record in C#, JavaScript, whatever. Okay? So there's nothing new about those. You're familiar with those. But the other thing, which is you're probably unfamiliar with, is what you might call an or type or a choice type. So let's say you want to have a snack, and you want to say you want to have an apple or a banana or a cherry. Now that's harder to represent in OO, but in functional programming, you would say it's an apple or it's a banana or it's a cherry. You can actually write a type that represents these 3 choices. Kind of like an enum. If you're used to enums, it's like enums on steroids. So, these are not really available in OO languages, but they are available in functional programming languages. So let's look at a real-world example of how you do composition. Let's say that you need to do a payment system. And you have 3 kinds of payments, and you have cash, you have checks, and you have credit cards. Right? And there's different information for each case. So how would you implement this if you were writing some code? Well, if you were an OO person, you'd probably create some sort of interface, payment method interface, and 3 different subclasses or implementations of the same interface for the different kinds of things you can do. So that's fine. That's the OOP style. In a functional programming style, you'd probably do it very differently, which is you'd build up a bigger thing from a set of smaller things. So you start off with some basic types, like a check number and a card number or something. This is like primitives. And then you take those and you build them together. You make, say, we have a card type, that's a choice. And so a credit card is a record, which has 2 different things in it. Right? So there's a choice type, and there's a record type. And then we take those, and then we say, well, a payment method is either cash or a choice. If it's a check, there's some check number information associated with it. If it's a credit card, there's credit card information associated with it. And there you go, that's a payment method. And you've got your 3 choices right there. And then you can keep going. You can say, oh, well, let's define a payment amount, which is a decimal, and a currency, which is a choice between euros and dollars. And then we can build a final thing, which is a payment. There's a record, which has an amount, and a currency, and a method, and so on and so forth. There's another record type. So what we've done here is, in about 15 lines of code, we've built quite a nice domain model all in one place. In one file, we didn't have to go to 20 different files to look at different subclasses. And it's built from using composition, using bigger types and smaller types. So it's a very different approach from object-oriented design. So one of the things we tend to do in statically typed programming languages is use static types for domain modeling. You can do all sorts of cool things with static types, and for documentation, you can see it's very clear how that code works. Obviously, it doesn't work in Clojure, JavaScript, or languages which are dynamically typed. It's a really big topic. I don't have enough time, and I have a whole book about it if you're interested. So I have a domain modeling made functional book. Right, let's go to the first pattern. So the first pattern is functions as parameters. And the guideline here is really parameterize all the things. Every time you see something, try and parameterize it. What do I mean by that? Well, here's some code to print a list of numbers. And you look at this code and you say, I've hard-coded the numbers 1 to 10. That seems really kind of strange. Why would I hard-code it? Let's make it into a parameter, okay? I'm going to parameterize. I'm going to pass in a list of numbers. And for each item in the list, I'll print it. That's much nicer. That's a much better way of doing it. And I think we'd all agree with that. But a functional programmer would look at this print and they say, you've hard-coded the behavior as well. What happens if you don't want to print it? What happens if you want to do something else? So let's pass that in as a parameter. So now I have passing in an action to do with each item as well as the list of items. So I've parameterized 2 things, but in particular I parameterized the behavior as well as the data. And by doing this, we've actually decoupled everything. So this is not necessarily printing. We're literally just looping through a list and doing something with each item. Right? So it could be any action, any kind of data. Now, what's cool about a nice language is that you can do this without having to worry about what the type of the action is. I don't have to say what kind of action it is. It's like I just type it in. It's kind of like it looks very dynamic in F#. This is F#, but I don't have to worry what the type is. It's kind of nice. But let's look at C# as an example of how you might do this as well. So let's say you have 2 functions. One takes the product of a list of numbers, or actually the product up to n, and the sum up to n. Okay. Now here's typical imperative code using a for loop. What's interesting is there's some duplication. Right? We can see we've got a for loop in both cases, and we always say, don't repeat yourself. How can we refactor this to get rid of the for loop? Right? So what we're going to do is we're going to look at the common code. So the common code is the for loop and the return. And what's different between the 2 functions is that the initial value is different in each case, and the action each time through the loop is different. So what we're going to do is refactor and pull those out. So after parameterization, we now have a function which has an extra couple of parameters. One is the initial value, and one is the action that you take each time through the loop. And then the code now is much more generic. We have the initial value, we have the action, and we return this. So this is now completely generic code. And what's cool about this is when we use this to define product and sum, we're now much more focused on what's special about these functions. You know, the boilerplate has been removed, the looping has now been removed, and we can now focus on, you know, what's the initial value, what's the action. These are the things we actually care about when we're looking at the code. So this is a kind of built-in, this is a nice function to have built in. It's actually built into the C# link library. Very nice. Right, so there's the parameterized, there's the common code, the initial value, and the action. So parameterizing things makes things look a lot nicer. Now, one cool thing about functions as parameters is they act as interfaces, okay? They can provide instant abstraction, and let me show you what I mean. So let's have an interface, say, with a bunch of methods in it. And if you take the single responsibility principle to the extreme and the interface segregation principle to the extreme, basically you should just have one method in an interface, because that's the guarantee there's no collisions between them, you know. But a one method interface is really just a function. So rather than defining interface, we can define a function that says, give me an int and spit out an int. So that's my interface for this particular method, as it were. But what's cool about this is if we have a function like add2 or times3, they have the same signature. They take an int as input and spit out an int as output. But so any of these functions are compatible with my do something function. I don't have to say that they implement interface. It's like afterwards, you know, I don't have to go back and retrofit everything. So I need this interface. Let me just change all my code to use this interface. You don't have to do that. Functions are interfaces automatically. So that's really nice. I'll give you an example. The decorator pattern is a classic thing where you have an interface and you want to change something and keep the same interface by adding extra code into it. So let's say we have an is-even function. It's a kind of boring function. It takes an integer and it spits out whether it's even or it's a Boolean. So int to bool. And I'm going to represent it like a little railway track here. So let's say we want to log the input and we want to log the output. So we want to enhance this function with this extra logging capability. And meanwhile, preserve the same interface, as it were. So we don't have to inherit from any interfaces. What we can do is we can just take that function, stick another little function in front of it using composition, stick another little function behind it using composition, and then glue all these functions together. And then we can give that new function a name. We can call it is-even with some extra logging. And what's cool is this new function has exactly the same interface, it has the same signature as the original one. An int takes an int and spits out a bool. And so anywhere where I use the original function, I can use this new function as well. So what's nice is I didn't have to modify the original function, I didn't have to define an interface, I just took an existing function, I just glued some stuff onto it and made a new function. So that's very, very cool. It's one of the things that functions are great for. So, you know, this is one of the things. People say use interfaces if you want loose coupling, right? Interfaces are great. But if you use functions, you get loose coupling for free. So I would say use function parameters for loose coupling. It's even better. Right, pattern number 2, multiple parameter functions. So all the composition techniques work really well when a function has one input and one output, because then you can just kind of glue them together. But what happens when they don't, right? Then how does that work? So it's not going to work. But here's the good news, is that every function can be turned into a one-parameter function. And that's a really important part of functional programming. So let's say we have a function like this. This is a two-parameter function that adds two integers together. So I'm going to represent it like a little bit of a railway track, and it's an int, arrow, int, arrow, int. That means you take an int, and you take another int, and you spit out a third int. Now, you can also define this as a thing. So here's it, the same function defined as a lambda. So we're saying the add thing is this lambda expression. Okay? And what's interesting is when you look at it as a piece of railway track, it has exactly the same signature. And the third way we're going to do it is as a one-parameter function. So this is a one-parameter function that returns another function. It returns another lambda with an extra parameter. And that looks like this, an int that returns an int function. Now these, what's interesting is that these are all exactly interchangeable. So a 2-parameter function, a 0-parameter lambda, as it were, and a 1-parameter function, you can turn any one of these things into any other of these things. And in particular, any function can be turned into a 1-parameter function. So if you have a 2-parameter function, you can turn it into a 1-parameter function. And then you can do all these great composition techniques with it. So that is typically called partial application. So let's say we have, here I'm printing my name, and the print function has 2 parameters. It has the format string, and then it has the value that you want to format, right? So it's a 2-parameter function. But that's not very helpful in terms of reuse. So what I'm going to do is I'm going to take the print function and the first parameter only, right, that whole thing, and that is now a 1-parameter function. And I'm going to forget about the second parameter for now. And then what I can do is I can assign that thing to because it's a thing, I can give it a name. I can call it hello. And then I can now reuse, now I've got some reusable code. I can reuse this hello with my name or with somebody else's name. So without doing any extra work, I've now got kind of a reusable piece of code. I didn't have to create a subclass or anything like that. I could just use it straight away, just using partial application. So it's really, really important technique in functional programming, partial application. Let's use it with some lists. Okay, so there's a partially applied print function. I've got a list of people's names, and I'm going to say for each name in the list, I'm going to use this hello function. So the list iter is just iterating through the list. Or I can have some partially applied arithmetic, adding 1 and equaling 2. Notice that both of these are missing the second parameter. Right, so there's another parameter that's going to come in later on. And so for each number from 1 to 100, I'm going to take each item in that list and add 1 to it, and then I'm going to take that list and I'm going to filter it by the second thing. So that little pipe operator, by the way, in F#, that's just like Unix pipes. It takes the output, it takes one thing and pipes it into the next thing, and then pipes it into the next thing. So this is how you do, this is typical functional programming. Now, if you've used link in C# or using streams in Java, you're probably familiar with this, but this is functional programming. This is why functional programming is very nice. Right, third pattern is bind. So bind is also known as flat map. Sometimes it's called and then. There's lots of different words for this thing, but it's really the concept I want to get across, not the actual word. Bind is the word that Haskell has used, so if you want to be cool, that's the word you should be using. Right. So what do we need bind for in the first place? So I'll give you an example, a couple of examples with what I call the pyramid of doom, or somebody else called this the pyramid of doom originally. You often see the situation where you do something, and if it's null, if it's not null, then you do something else, and if it's still not null, then you do something else, and so on. And if it's still not null, you do something else. So you do this kind of thing where you chain together all these kind of tests. And then, at the end, you have to return null everywhere. So all these nested null checks are really horrible, right? I think we can all agree this is that code looks really bad. Bad cyclomatic complexity, all sorts of bad stuff. You can always see this kind of thing when you see this pyramid, right? This is the pyramid of doom. Your code goes in and in and in and in, and then comes out and out and out. So in some languages, you can do early returns to avoid this if you're just doing a bunch of guards or something. But in some situations, you can't avoid it. Like if you're doing tasks or something like this, you start a task. When the task is finished, you want to do another task. And when that task is finished, you want to do another task. And when that task is finished, you want to return the result, and so on. You can't short-circuit that. You have this ugly code. You can't really avoid this kind of ugly code. Right, this nested callbacks. Again, we have this pyramid of doom. So this is both this kind of code. We all agree it's really ugly, but it's not obvious how you can fix it. So let's fix the first example with the nulls. Now, in functional programming, we tend not to use nulls. We tend to use the option type. So if you're not familiar with that, an option is basically it's either something or nothing. It's just a choice between two things. So let's replace it with the option type. There you go. If it's something, do something. If something, no. No, that's not any uglier. It's not any more elegant. It's really ugly. We haven't really solved the problem by using an option type. But there is something we can notice. There's a pattern here when in our nested code, which is that every time we something, we do something with that value, and otherwise we do nothing. If it's something, do something, otherwise do nothing. If it's something, do something, otherwise do nothing. Okay, so that's the pattern. How can we exploit that pattern, right? Well, the answer is, here's the pattern. I'll just kind of zoom in on this pattern. If it's something, do something, otherwise do nothing. And you could have a null equivalent. If it's not null, do something. If it's null, just return null. So that's the pattern we want to sort of codify. And what we can do is, what exactly is it we're going to do with this thing? Well, we don't know. It could be anything that we do with this value. So let's parameterize it. Let's write a little helper function called if sum do. If it's something, do something. All right? And what we're going to do is exactly the same code as before, but we're going to have a parameter, a function parameter like that. That is we don't exactly know what you want to do with it, but you're going to pass in that function, and that function will decide what you actually do with the value. Right? So that is a parameterized version of this. Now what's cool is when you have this if sum do function, you can take the original code and just say if something, do the next thing. And if it's still something, do the next thing. And if it's still something, do the next thing. And what we've done now is we've taken the ugly pyramid, this super nested stuff, and we've turned it into nice linear, straight up and down, much easier to understand. Okay, so this code is a lot easier to understand thanks to this little helper function. Right? So hopefully this little helper function makes sense. It's very easy, just a couple of lines of code, but it makes a huge difference to the readability of your code. And this is actually an example of a much more general problem, which is what bind is all about. You often have this situation where you have some sort of input, and you have some sort of successful output, but you also have something else that kind of messes it up. So in this case, it's either something or it's nothing, and in other cases, we'll see some other cases where it's the same kind of idea. So we have all these things, and we want to connect them. When it's something, do the next thing, and when it's nothing, do bypass. Right? So if this was a toy railway track, I think it's obvious how you would connect these two little bits of track, right? Sometimes it's good to go back and pretend you're a child. If you're a child, you'd say, well, okay, how do I combine these things? I just combine them like that. I turn them from a bunch of little points or switches, whatever you want to call them, into a single two-track system. And every time you go onto the red track, you kind of stay on it. Right? So that's the before and that's the after. So here's the problem, which is that we have these little one-track functions, and if we want to compose them together, we can do that. That's easy. We just connect the inputs and outputs. And if we have two-track functions, we can also compose them together. We just connect the top output and the bottom output. But we don't have that. We have these things with one input and two outputs, and they don't compose. That's the real fundamental problem here. So how do we combine these mismatched functions? And this is where bind comes in. Bind all the things. Functional programmers love to use bind. So if you want to pretend like you're a cool person, you can just say, I know what bind is. You can just do the secret handshake, So bind, or flat map. So here's the problem. We have a one-track input and a two-track output, and it's not composable. If we could turn it into a two-track input and a two-track output, that is composable. Those, we can do that. So what we want is a function adapter, something that takes the first kind of function and turns it into the second kind of function. So if we have this kind of function adapter, we can get what we want, which is the nice composition. So here is our function adapter. Again, using the railway analogy, it's like a little thing, and there's a little slot at the top, and you stick the piece of railway track in, and it converts it for you. So we're going to stick our points or a switch function, we're going to stick it in the top, and it comes out as a two-track function. So that's exactly what we want. That's it. So let's look at the implementation. The implementation says, well, you give me input, and if the input's something, I'm going to call the next function. And if the input's nothing, I'm just going to keep going. Right? Now, this code is very familiar. This is exactly the same code as we just did with the if something do function. It's exactly the same implementation. So let's look at it to chain options. So before, we have this kind of ugly pyramid of doom thing. And afterwards, we write a little bind function. And like I said, it's exactly the same as the if, sum, do. We have our function parameter that we pass in, and we decide what to do with the value based on that function parameter. And then once we have this bind, we can say, do something, and then bind it to the next one, and then bind it to the next one, and bind it to the next one. So there's bind used in the context of options. No pyramids. Nice and linear and clean. So you can see this is why bind is so cool, because it makes your code really nice. And technically it's called monadic bind, which is the jargon word there. Now let's look at another example, which is chaining tasks together. So tasks, promises, futures, asyncs, I don't know. There's lots of different words for these things, and they're all slightly different. But this is the basic concept. We have something which is running. When it's finished, we want to do the next thing. And if it doesn't finish or it crashes the thing, then we just want to cancel. Right? So how do we do that? Well, we do the same thing. We want to combine these little railway pieces together. And we're going to, this time, here's the one before with the kind of the ugly pyramid. And we're going to create a bind which is specifically for doing with tasks. So the task bind says, well, you run a task, and when it's finished, you do something with the task result. But I don't know what it is you want to do, so I'm going to let you pass it in as a function parameter. So you tell me, you pass in a parameter, you tell me what you want to do, and then that will be the next step in the chain. So that's the task version of bind. And again, we can rewrite the code. We start a task, we bind it to the next task, we bind it to the next task, and so on and so forth. Again, we've got rid of the nested thing. We have a nice linear implementation. So that's another monadic bind for you there. And one really useful thing about bind is you can use it for error handling. So you often have a nice piece of code when you start off. You say, well, let's say this is like updating a customer, for example, on a website. You get requests from the input, the HTTP request. You validate it, maybe you uppercase the email. You update the database, and maybe you send an email back to the customer saying you've updated it, whatever it is. It's really nice like this. The problem is we don't have any error handling. So what happens if it doesn't validate? We need to say, okay, it's not valid. What happens if the database doesn't work? Well, okay, we need to have a special case for that. What happens if the customer's record's not found? What happens if the database connection fails? What happens if not authorized? What happens if the email server is not available? All this stuff. So your nice, elegant code, we started off with 6 lines of nice, clean code, and now we have 18 lines of ugly code. So we have, in 2/3 of the code is error handling, right? And I'm sure you've all seen this. Your error handling code takes up most of your code, and it's kind of annoying because it interferes with the kind of understanding of what's going on. So how can we fix this? So in functional programming, one of the things we use is a result type. And a result type is designed to handle when you do something and it either succeeds or it fails, right? So we can just define that as a choice. If it's either yes, it succeeded, okay, or no, it didn't succeed, and it's an error. So it's a choice type, very useful. And then we use it in code like this. We say, if we're validating something, say if the name is blank, that's an error. If the email is blank, that's an error. Otherwise, it's good. So this is a typical little bit of validation code that you might have in your web application. So you have, validation code looks like this. Maybe updating the database looks like that. Maybe sending an email looks like that. You have all these functions that look very familiar now. And how do you connect them together? You connect them together in the same way. So this error handling approach is really, really nice. You can make the errors really explicit in your code. And I call this railway-oriented programming. That's my name for it. I have a whole thing about that too, if you're interested. If we look at the original code before the error handling, we can see that it's nice and linear. We say, take a request, and then validate it, and then canonicalize it, and update the database, and so on and so forth. So that's the before code. Now let's look at what the code looks like afterwards, okay? One of the things is that we don't have any error handling, so it's just like, you might think of it as a sort of a single track. There's no errors whatsoever. Now afterwards, with the error handling, this is what the code looks like. Okay? It looks exactly the same, which is nice, because it's really focusing on what the actual steps in the process are. But how can it look exactly the same and still have all the error handling in it, right? Well, the answer is because these are now two-track functions, not one-track functions. And if we connect the two-track functions together, we get all the nice things about error handling, but we still can see, at the top level, we can actually see all the different steps in the process without kind of contaminating it with all that stuff. So there you go, that's error handling. And like I say, I have a whole talk about that. So this brings us to monads, the terrible jargony word that everyone hates. A monad is really basically just a data type. I'm getting some feedback here. A monad is basically just a data type with a function that goes along with that data type, which is bind or flat map or whatever. So we saw with the option, we had an option bind. With the task, we had a task bind. With the error handling, we had a result bind, and so on. So that's all it is. A monad is a data type and a function and some sensible implementation. We call that the monad laws. That's just, the monad laws is just another way of saying we've got some sensible things. It doesn't do something too stupid. And another jargon word is a monadic function. So a monadic function is like a switch or points function using bind. So now you all know what a monad is. It's not too scary. It does sound strange, but there you go. So why are functional programmers so big on monads? The reason is because it's a general purpose way of composing functions which have complex outputs, like tasks or errors or whatever. So monads are very big because you have this kind of situation all the time, and you can use monads to solve that problem. Right. Fourth pattern, which is map. Let's take a drink here. Right, so another situation you have a lot is that we have this kind of world of normal things, integers and strings and dates and booleans and whatever. And you have a sort of a parallel universe where everything is transformed into something. Like instead of a normal int, you might have an optional int. Or a normal string, you'd have an optional string. Or a normal bool, you have an optional bool. And you have these two different worlds. And you find often that you kind of get transported into this other world. You have something and it returns an optional string or an optional int. And then you have to come back down to the normal world to work with it. And then you go back up. And then you come down, you go back up, and so on and so forth. This is kind of ugly, again, just kind of up and down all the time. And generally that's considered bad practice in functional programming, to go up and down all the time. What you really want to do is go up to this other world and then stay. Stay in this other world as long as possible and only come down at the very end when you're finished. Right? That's the best way of doing it. So let's look at an example. Here's add 42, because 42 is a good number. And if we take that function, we add 1 to it, we get 43. So that's a kind of a normal, boring function that works in the normal world. Right? It works on non-optional values. Now, if we want to add 42 to an option, what we have to do is say, well, is it something or not? If it is something, we can get the value out and we can take the new value, and then we have to take the new value, we have to rewrap it up and turn it back into option again. Otherwise, it's left what it is, right? And again, you could replace this with nil if you want to do nil checking, same kind of thing. So we're unwrapping it, we're doing this thing, and then we're rewrapping it up. So again, kind of ugly, going down, doing something and going back up. We really want to try and avoid this if we can. So how can we avoid this? Well, what we want to do is have this add 42 somehow transported into this other world. Right? If we could have this add 42 transported into this other world, we could use it there without having to come back down to our normal world and work with it. So that's the problem we want to do. How do we stay up there? Well, the answer is the map concept. So we have a function down in the normal world. We want to have a function in this other world which works with options. And we want to transform our normal function into this option function. And that's exactly what the map does. So a map transforms a function in one world into a function in the other world. All right, so we've got option map. Now once we've done that, if we look at this code again, we can get our add 42 to option, our new transformed function, just by using option map on it. And once we've got the option map, we can then apply it to an optional value. So that's the right way to do this kind of stuff. You don't have to come down and go back up again. Same thing for lists. Let's say you have a function which works with normal things, and you want to transform it into a function that works with lists. Okay, so instead of having normal things, you have lists as input and lists as output. That would be list.map. And here's an example of that. We take our add42 and we use list.map, and now we have a new function which adds 42 to each element in the list. Okay, so if you pass it a list of numbers, we get a list of numbers back. And we can do the same thing with async. We have a normal value, function works with normal things. Let's say we have a world of async values or tasks or something, and we want to transform these values. Do exactly the same thing. There's an async.map. So most wrapped generic types, options, and lists and so on, they have a function associated with it, and really try and understand how to use it, because it's going to save you a lot of time. And if you write your own generic types, do write a map function for them, because that will save other people some time. And the functional people have a word for this too. They call this a functor. So another bit of jargon. So a functor is, again, it's a data type like an option or a list or something, and it's got a map function along with it. So that's all a functor is. So, okay, final pattern, which is monoids. So there's some mathematics ahead. I hope people aren't too scared of mathematics. Here's the mathematics. 1 plus 2 equals 3. Is that too scary for people? Hopefully not. How about 1 plus 2 plus 3 is the same as 1 plus 2 plus 3. And here's another one. 1 plus 0 is 1, and 0 plus 1 is 1. So if you can handle that level of mathematics, you can understand what a monoid is. Okay. So that's really it. Now, if we think like a mathematician and we look at these things, we say, well, that's actually some interesting stuff going on here. If we look at 1 plus 2 plus 3, what's going on is we've got some things, and we're adding them together. We've got some way of combining them. We're making another kind of thing of the same type. We start with 2 integers, and we end up with another integer. And that works for lots of other things. We can do the same thing for multiplication. We start with 2 things. We've got some way of combining them. We get another one of the same kind of thing. Or let's say strings. We've got 2 strings. We've got some way of combining them. We get another string. We've got 2 lists. We've got some way of combining them. We get another list. Okay? So that's the basic concept. And what's cool about this is because it returns another kind of thing, we can keep going. So if we have 1 plus 2, that returns another integer. Well, because that's an integer, we can add to it. And that returns an integer. And because that's an integer, we can add to it again, right? So what's very cool about this thing is a pairwise operation can turn into an operation that works on lists, right? We can actually work with any number of things just by doing pairwise operations one at a time. Now, the next thing we can look at is this thing of 2 plus 3 plus 1, 1 plus 2 plus 3. The order doesn't make any difference, right? That's very important. You can do the first thing, we can do the second thing. So we could say 1 plus 2 and 3 plus 4, or we can do 1 plus 2 plus 3 plus 4. How we do it, how we actually do the calculation doesn't matter. Now, this isn't true for other things like subtraction, right? It doesn't work for subtraction. The order doesn't matter there. Right, now the final thing is this 1 plus 0 equals 1. Now, if mathematicians say, oh, that's interesting, there's a special kind of thing that when you do the combination, it returns back the original thing, unchanged. So for multiplication, that special thing is 1. Right, that's the same thing. For string concatenation, that special thing is an empty string. That's the 0 for strings. And for lists, it's the empty list, and so on. So let's look at what we've got. We've got a bunch of things. We've got some way of combining them 2 at a time. We've got, the first thing is we've got this closure. When you return 2 things, when you add 2 things, you get another thing of the same type. The second thing is associativity, which is the order doesn't matter. And the third thing is there's a 0, there's an identity element, that when you add them, you get the same thing back. So those 3 things, that's all a monoid is. Okay, so if you can understand the basic math, now you understand what a monoid is. All right? So why are monoids, this is another thing that functional people like, why are monoids kind of talked about all the time? Well, there's a lot of benefits. If you've got a monoid, you can get a lot of stuff for free. So for example, this closure thing, the benefit is that you can take these pairwise operations and you can turn them into things that work on lists. So I could say if you have 1 plus 2 plus 3 plus 4, pairwise, then you've got a pairwise addition, there's a function called list.reduce, and that will take that plus operation and apply it to every item in the list. It's the same thing, so you can reduce things with a plus. If we have multiplication, 1 times 2 times 3 times 4, we can reduce the whole thing by applying multiplication to it. If we have, let's see, string concatenation, we can reduce a list of strings using string concatenation. So this reduces, like I said, pops up over and over. Now the second thing, the associativity, has a lot of benefits too, because you can do things like parallelization. I'll show you what that means. So let's say you have 1 plus 2 plus 3 plus 4. Obviously it's a very simple sum, but if you had like 2 CPUs, you could do the 1 plus 2 on one CPU and the 3 plus 4 on the other CPU, and then you could combine them together. So you can distribute a job over multiple CPUs or multiple machines on the cloud. So if you have a monoid, you get parallelization. And you also get incremental accumulation. So let's say you've calculated 1 plus 2 plus 3, and then the next day your boss comes and says, oh, can you do 1 plus 2 plus 3 plus 4? And you say, oh, I have to start all the way from the beginning and add them all together again. Well, obviously you don't. You can remember that you calculated 6, and you can start from 6 and just add the next piece. Right? Now that's a benefit of a monoid. And if you do have things like an empty list, or you have a divide and conquer algorithm and you don't know what to do for empty steps, that's what the 0 is for. It's the initial value for empty data. So I'm sorry I'm going a few minutes over. I'll just be another couple of minutes. Right, so let's look at some examples of simplifying some code with monoids. So let's say I have an order line with a quantity and a total, and I have a bunch of order lines, and I want to add them up. Now I could just write some imperative code to add them up, but if I'm a cool functional programmer, I would say, well, that's interesting. A combination of monoids is another monoid, so let me know that it's a monoid. Let me just write a pairwise operation. So I'm going to combine the two things pairwise. And now that I have a pairwise operation, I can just reduce the list using the pairwise operation, because that's the cool way of doing it. So there's an example of how you can get some benefits straight away from knowing it's a monoid. Another very common pattern is to convert non-monoids to monoids. So let's say you have a bunch of customers, and you want to add up their information. Well, it doesn't really make sense to add up their information, but you can add up their statistics, their usage statistics, and so on. So what you're going to do is turn each customer into a statistics object. And then once you've got the statistics objects, you can then add them up in the same way that we added up order lines. Right? And that is a monoid. So what you do is you convert something which isn't a monoid into a monoid, and then that's using map. And then you can take all those monoids and sum them up using reduce. And that's a map followed by a reduce. Okay, you've probably heard of that. So this is what Mapreduce is. It's really just mapping something and then reducing it because it's a monoid. And if you're used to Hadoop, someone posted this very funny tweet. It says, Hadoop, make me a sandwich. And the original problem is you have all these ingredients. You have a piece of bread and a piece of lettuce or something. You can't combine them. But what you can do is you can map them to sliced things. And then once you've got the sliced things, you can reduce them into sandwiches. So there's the Mapreduce, as a deli function. So once you start using monoids, you really start seeing them everywhere. You start seeing this is a monoid, this is a monoid. So for example, there's a famous metrics guideline. If you're doing DevOps, one of the guidelines is use counters rather than rates. And if you think of it in terms of monoids, once you say, well, this is a monoid, just make sure your metrics are monoids. That's exactly the same thing, because it means you can do incremental updates, you can handle missile data, you get accumulation for free, you get parallelization for free, all that stuff. So that's very good. Now, function composition, you might say, well, this sounds awfully like monoids, this function composition. If you combine two functions, you get another function. It's not exactly the same because the inputs and outputs might not be the same thing. So function composition normally is not a monoid. However, if the input and output are the same type, like an apple input and apple output, and you combine them, you get another function, which is an apple input, apple output. So yes, that is a monoid. So that's cool. So those kinds of functions can be used as monoids. So just one final thing. We've talked about monads, which is a jargon word. We've talked about monoids, which is another jargon word. It's kind of confusing. But there actually is a connection between the two. If we think about these little bits of train track, I talked about you can combine them together and you get another piece of train track. Right, so that's the same kind of thing. We've got the closure going on there. And if you combine two pieces of train track, it doesn't really matter which order you combine them in. So that's the associativity going on there. And we've got the identity, which is just doing nothing. So you can actually combine these kinds of functions like a monoid. Right? So the monad laws, which I talked about, these are making things sensible for monads. It's actually just the same thing as the monoid laws in a sort of different guise. And of course, if you break the monad laws, you go to jail, but you also lose these benefits such as aggregation and so on. So, as I said, a monad is a kind of monoid, sort of, kind of. And there's the jargon word. A monad is just a monoid in the category of endofunctors. That's the jargony way of saying the same thing. So, we talked about partial application for composing functions. We talked about bind and monads for composing functions. We talked about map and functors for composing functions. We talked about monoids, which is another way of composing things. Notice composing. We see this over and over again. This is really composition everywhere. So all these things are really just tools that allow you to do composition. So that's all you have to understand. And that is it. Thank you very much. The slides will be on my website at FP Patterns. And if you want to know more about F#, you can go to fsharp.org. So thank you very much.